Hi class, we are on chapter 3.3, modeling with systems of equations. This is the last section in chapter 3, and then we're going to move on to chapter 4, which covers methods of solving higher order DEs. So differential equations that are second, third, fourth, etc. order, right? So for this one, right, we're going to create systems of equations. So just like a system of linear equations, they're all going to be related to each other. It's going to be several equations that model different aspects of the same system, but all together they model the system, right? So one's not going to work without the other. So we're going to have several equations that we're working with, several DEs, and generally it's still going to be one solution, right? However, we don't have methods of solving systems yet, right? So we're not going to actually solve anything. We leave solving systems for the end of section 4, and then we cover them in chapter 8. So later on down the road, we will sit down and really talk about solving these. They'll pop up again, like I said, in a couple of sections. We'll have a couple of little, honestly, to me, weird ways of solving them. And then we'll talk about like the more standard methods of solving systems, right? So, chapter 3.3, let's get started. So again, as I said, we do not yet have the tools to solve systems of equations of DEs. So we're really just going to focus this section on creating the models, right? So once we're able to create models, once we learn how to solve the systems, we can then do like we did earlier in the section and create the models and then solve them, right? So the first one we're going to talk about is radioactive decay. So let x of t be the amount of a substance x at time t, right? So the derivative of x with respect to time, right, is going to be a constant multiple of x, right, some proportionality constant that's negative because it's a decay, right? So here we're saying that x is going to decay into some substance y, right? It loses electrons. It's going to turn into something else eventually, right? So x loses atoms. Here, the rate of change, right, the derivative of y with respect to time, right, as y decays, it is gaining electrons that x is losing, and it is also losing its own electrons, right? And it's decaying into a new substance, z, right? So the rate of change of z, right, instantaneous rate of change, the derivative of z with respect to time, is equal to some constant of y, and it is gaining electrons from y. So x decays into y, right? And as it does so, it loses atoms. Y decays into z, and as it decays, it is gaining electrons from x, but losing its own electrons, okay? Most likely at different rates, right? And then z is just gaining electrons from the decay of y. So here we have three differential equations, and they're all related to each other, and they all model a single system, right? Which is x decaying into y, decaying into z. We have a notation for that as well, right? So x decays into y and loses electrons at a rate of negative k, or with respect to the proportionality of negative lambda 1, and y decays into z, losing electrons with the proportionality constant negative lambda 2. Okay, so that would be the notation for that. The next model we're going to talk about is the predator-prey model, right? So in the last section, we did quite a bit with the predator-prey, with the logistics. So now we're going to talk about these predator-prey models, these decay and growth models, right? Populations, as a predator-prey. So here, the derivative of x with respect to t is going to be negative a times x. So we got a negative proportionality constant. So this will model predators in an environment where there are no prey. It is going to decay. If there's nothing for a population to feed on, then that population will begin to die out. Okay. Here we have a prey model. Y is my equation that models the number of prey elements that I have in an environment at time t. If there is no predators to prey on the prey to eat this food source, then they are just going to grow. They don't have to worry about anything. It's fine, dandy, right? green grass and sunshine and rainbows, right? There's nothing for them to worry about. Their population is just going to grow, right? Ideally to some sort of carrying capacity, right? Here, this is the equation that we're going to have when my predators and my prey interact, right? So remember, y represents the prey, x represents the predators. So I have my decreasing values here for my predator model, but they are going to increase in population with respect to some constant times the number of interactions between the predators and the prey, right? So ideally, if this is a large value m here, then there's lots of interactions, then the predators get to eat lots of prey, right? If the prey is bountiful, they're going to eat a lot, and they're going to grow, and they're not going to decay as fast, right? Or this function may overtake this function, especially since this is a product of two variables, right? Whereas, so this may not, if there's a lot of prey, this will not reduce, it'll be negligible the amount that it reduces to the function, right? Is what I'm trying to say. Here, this is a model where the prey is again having interactions with predators, right? So they're going to decrease based on the number of interactions that they have with the predator. So obviously, the more predators that are around, the more that this is going to take away from this growth rate of this amount. Okay, so this is called the Lotka-Volterra predator-prey model, right? This system here. So again, the predators and the prey are within the same system. So the predators get to have interactions with the prey, and the prey have interactions with the predators. So if two populations are competing for the same resources, so this is not predator-prey, but maybe two types of birds that are trying to get the same source of seeds, for instance, right? Then our equations are going to change a little bit because we no longer have one population preying on the other, right? So here we're going to have two growth models, right? Because there's not one preying on the other, but they're going to decrease based on how many interactions they have with each other, right? So now we have the isolated logistics growth. So here I have the rate of change of x with respect to t is ax minus mx squared. So this is very similar here, except you're kind of looking at the number of interactions with itself, right? So a population is competing against itself for resources. When two isolated logistic populations interact with each other, then we get this following system. So we have the logistics growth of one where it's competing against itself. This one is competing against itself as well, but they are also competing against each other, so you have this secondary term being subtracted from the rate of change. Okay. So example, let's consider the series circuit that we have here. We have an LRC series. Here, this series is broken into parallel, right? So here we have the current goes through an inductor and then a resistor, but it splits here and it also goes across a capacitor before it comes back to the output source, right, or the input source. So the voltage across the circuit can be modeled by the voltage across each separate loop. So around this loop and then around this loop. Okay, so inductance and resistor plus inductance and capacitor. I'm sorry, that's not what it is. So inductor and then across this as well as across this, right? So we're asked to write the system in terms of I1, right, of t and I sub 2 of t. So I'll fix this in the write-up. This should be a D here, obviously. So note that I splits across into two different currents, one that goes across the resistor and one that goes across the capacitor. So we have an LR loop and an LC loop. For the LR loop, we have E of t is equal to L times the charge on it, which is the derivative of I, right, which is going to be Q, over I times R, which we know this is also, this is the second derivative of Q, this is the derivative of Q, right? For the LC loop, we have the same thing, the same term, but then we have that capacitance term, so the charge over 1 over the capacitor. Now, what we want is we want to write this in terms of I1 and I2, right? So it doesn't make sense for me to have Q anywhere, because anywhere I have Q, I know that Q and I are related. So wherever I have Q, I should have an I, right? And if you notice, this Q over here, this is actually a charge coming from I3. So it doesn't really make sense for me to even have this term here, because it's not actually written in terms of I1 and I2. It's actually written in terms of I1 and I3 of some form, right? So the problem here is that Q is in terms of I is actually I3. So what I'm going to do is I'm actually going to subtract these two equations together, right? The E of t is going to cancel, and the L di1 over dt is going to cancel as well, and I'm going to get I2R minus 1 over c q. Okay, so we did what we normally do in algebra, and that's try to eliminate some stuff, right? Now the problem is I still have q in terms of I, right? I3 in this case. So I want to make some manipulations here. Okay, you can start to solve for q. So now I have q in terms of I, and I2 in fact, right? So if I take this derivative, I can then differentiate this. Remember, c and r are constants. I is a function. So I get dq over dt is cr, and then the derivative of I2 with respect to time. Okay, so note that for LC, the LC loop, the voltage over the capacitor is going to be 1 over c times q, right? Which is what we got from here. Is going to be the same thing as the derivative of 1 over c q. I'm sorry, that's not going to be the same thing, but that's going to imply that this derivative is 1 over c dq dt, right? This dq dt. So I know that this charge over c is I3, so I can replace this with I3 over c. Okay, therefore I3 is dq dt. Okay, because I took this and I took the derivative. So if I'm looking at just this term and I differentiate just this term, this is what I got, right? So I know dq dt is cr di dt. So really what I'm doing is I'm creating a relationship here where I'm trying to tell you that I3 is this result, right? dq, the derivative of dq dt is really just I3, and so that means that I3 is cr, the derivative of it with respect to t, right? That's all I'm saying. I3 is this thing, right? So we also know that I1 is I2 plus I3. Okay, I1 is I2 plus I3. I1 splits to I2 and I3. So if I try to isolate I3, I get I1 minus I2. Okay, so I1 minus I2 equals I3. This is I3. Right? Therefore, if I zero this out, this is the relationship that I have. Okay, and so that is my second equation, right? E of t is 1. It's in i's, I1 and I2. And then my second equation is now in terms of I1 and I2. And so now I have a system of equations written solely in I2s and I2s. There's no q's. I3 is not present, or neither are any terms that are associated with I3. Okay. So another example. Oh, our favorite, right? Water coming in and water coming out. So here we are going to need to have, how many equations do you think? You're right, 3. One for this tank, one for this tank, one for this tank. So we're going to write equation for this tank with what's coming in and what's coming out. We'll write an equation for this tank for what's coming in and what's going out. And we'll write an equation for this tank for what's coming in and what's coming out. So remember, the equation for any single tank is rate in minus rate out. So I need to figure this out. But notice this, okay? In I have 4 and 2. So in I have 6, out I have 6. It's in equilibrium. Here I have in 6, in 1, so that's in 7, 2, and 5 out. So 7 in, 7 out. This is in equilibrium. Here, 5 in, 1, and 4 out. So here, I'm also in equilibrium. Okay, so none of these will ever drain. This will never be empty while these are full, right? They're all going to stay full, basically, right? So I want to construct a mathematical model for the number of pounds of salt, x1, x2, and x3, all of t, at time t in either of the tanks A, B, or C, right? So this tells me how much is in A, this tells me how much is in B, and this one tells me how much is in C, right? x3 for C, x2 for B, x1 for A. Right. So we're going to create this equation just the same way we did before. The rate of change of x1 over time. So in, okay, I have 0 coming in, right? 0 times, the concentration is 0 times the amount that's coming in. So 0 times 4, 0, plus 2 times x2 over 100. So 2 in, right? So n is 4 and 2, so 0 times 4. And then 2 times the concentration that's coming in, right? So whatever that function is over 100, right? Because that's how much the tank holds, right? So for this one, n is going to be 6 times whatever was in here, right? Which is x1. And then whatever was in here, so that's going to be plus x3 over 100, and then minus what's out. Okay, so 0 plus, so this is in because it's plus, right? So 2 times whatever was coming from tank 2 divided by 100, because that's how much fluid is in tank A total. And I'm going to subtract from that what's coming out, right? So however much solution is coming out times the rate that is coming out. Okay. So when I simplify this, I'm going to get 2 and 100 is 150. 6 over 100 is 3 and 50. Okay. For the second tank, same thing. So again, I hope you drew this picture out, or you're looking at the notes that I have for you so you can see what this picture is, right? So what do I have coming in? 6 times x1 over 100, right? 1 times x3 over 100. 6 times x1 over 100 plus x3 over 100. And then what's coming out? Well, out I have 2 times x2 over 100 and 5 over x2 over 100. Okay, so out 2 times x2 over 100 minus 5 times x2 over 100. Then I can simplify these as well. So 3, this is still 1/3, this is 1 over 50. Sorry, I add these together, so that's a negative 7 over 100. Okay, instead of doing over 50 and then adding them. So I have that, right? From there, I can do the same thing for the x3. So maybe you pause it right now, and you come back to, or you come back to here right now, and you pause it, and you create your own equation for x3 and see if it's going to be the same as what I'm coming up with. So I'll give you a chance to pause it now. Hopefully you're back and you wrote this equation. So let's see what you have for x3. Okay, so for x3, 5 times x2 over 100. So in, and then our out, right? Minus what else we have coming out going into the other, into the tank, and then coming out, period, right? So simplify that, and then this is our system. So I have my simplified for my rate of change of x1, my simplified form for my rate of change of x2, and my simplified form for my rate of change of x3.